Welcome to For Science Salah Lotfy channel. This short video is dedicated to expressing our deepest gratitude and sincere appreciation. On behalf of myself, Professor Dr. Salah Lotfy, and the entire team behind this channel, I would like to extend special thanks to a distinguished figure in the nuclear energy field, Professor Dr. Tarek Farouk Nagla. Professor Dr. Tarek Nagla is the former research scientist at the Nuclear Power Plants Authority in Cairo, Egypt. His lifelong dedication to nuclear science and engineering has inspired generations of researchers and professionals. His invaluable scientific contributions to our recent video series on nuclear energy have enriched both our understanding and the content I deliver to you, my valued viewers. It was through his expert guidance and generous support that I was introduced to one of the most important references in modern nuclear science, Introduction of Thorium in the Nuclear Fuel Cycle, short to long-term considerations, published by the OECD's Nuclear Energy Agency in 2015, report number NEA number 7224. This foundational study is now the core of our ongoing video series exploring the potential of thorium as a nuclear fuel, its advantages, and its role in the future of sustainable nuclear energy. Professor Dr. Tarek Nagla, your contribution is not only appreciated, it is instrumental. I thank you from the bottom of my heart for your trust, your insight, and your belief in the mission of this channel. I will continue this scientific journey in your honor, and I invite all my viewers to stay tuned to the For Science Salah Lotfy channel as we unfold this exciting series, built on the solid scientific foundation you've helped us establish. Don't forget to like, subscribe, and share. Science deserves to reach everyone. Hey science fans, welcome to the For Science Salah Lotfy channel. Today, let's talk about a game changer for the future of energy: thorium. We need clean, reliable energy, and nuclear power has long been a major player. But what if there's an even better option than uranium? Enter thorium. Named after the Norse god of thunder, thorium is super abundant. There's 3 to 4 times more of it in Earth's crust than uranium. That means less worry about running out of fuel and more energy security for the future. As we move away from fossil fuels, thorium could help us fight climate change with less radioactive waste than traditional nuclear power. It's also much harder to weaponize, making it safer for global security. Thorium isn't about replacing uranium overnight, but about expanding our options for a flexible, robust energy system. It's a scientific adventure, full of chemistry, engineering, and the potential to make the world better. So, what makes thorium so special? Let's dive in and see how this element could power our planet for centuries. The journey starts now. Imagine the possibilities. Before we dig deeper, let's thank the scientists and engineers who paved the way for thorium research. Our knowledge comes from decades of experiments, research, and international collaboration. Reports from organizations like the IEA are packed with data from experts worldwide. Every discovery about thorium, from geology to fuel fabrication, builds on the work of these pioneers. Their dedication is the foundation of everything we're exploring today. Science is a team effort, and we're part of a long story of discovery. Let's honor their legacy by learning all we can. Now let's get into the details. Here's a key concept: resources versus reserves. Resources are the total estimated amount of thorium in the Earth's crust, millions of tons. Reserves are what we can actually mine profitably right now, using today's technology. If prices rise or technology improves, more resources can become reserves. So when you hear about massive thorium resources, remember, only a fraction is ready for use today. Understanding this helps us plan realistically for the future. It's all about turning potential into practical energy. Let's see where the world's thorium reserves are concentrated. India leads the pack, with around 850,000 tons, thanks to its rich coastal mineral sands. India's long-term nuclear program is designed to use thorium as a primary fuel. Other major players include Brazil, Australia, the United States, and Egypt. The US has deposits in Idaho and Montana. Australia's reserves are often found with rare earth elements. Many other countries like Turkey, Venezuela, and Norway also have significant deposits. Thorium's global spread means more countries could achieve energy independence. Unlike uranium, thorium is more evenly distributed, promising a more balanced energy market. The global map of thorium is a map of opportunity. Who will lead the way? So what does thorium look like in nature? It's mostly found in a mineral called monazite, a reddish-brown phosphate packed with thorium and rare earths. Monazite forms in igneous and metamorphic rocks, then gets concentrated in coastal sands and riverbeds over millions of years. These placer deposits are nature's way of pre-sorting valuable minerals for us. Other thorium-bearing minerals exist, like thorite and alunite, but monazite is the main commercial source. It's often mined for rare earths, making thorium a valuable co-product. Understanding these minerals is the first step from rock to reactor. The journey starts in the sand. Let's see how we get thorium out. Here's a cool fact. Almost all thorium today is a byproduct of mining for titanium and zircon. Companies mine heavy mineral sands for ilmenite and rutile, for white paint pigment and zircon. But monazite comes along for the ride. For years, monazite was considered waste, but now it's recognized as a valuable source of thorium and rare earths. The existing mining infrastructure means we don't need to start from scratch to get thorium. We can piggyback on the titanium and zircon industries, making thorium extraction more economical. The cost of mining is already covered by the main products. Thorium and rare earths are valuable bonuses. This is industrial symbiosis at its best. Waste from one industry becomes fuel for another. Next time you see white paint, remember, it might be linked to future nuclear fuel. Let's see how we turn this raw material into reactor-ready fuel. Once we've extracted thorium, we need to turn it into nuclear fuel. The most common form is thorium dioxide, or thoria, a ceramic with a super high melting point. Thorium isn't fissile, but it's fertile. It absorbs a neutron and becomes uranium-233, which can sustain a chain reaction. To start the process, we mix thoria with a small amount of fissile material, like uranium-235 or plutonium-239. The challenge is blending these materials perfectly for safe, reliable fuel. Mechanical mixing combines fine powders before pressing them into pellets. Advanced methods like sol gel processing create uniform, perfectly mixed fuel at the microscopic level. The result? High-performance fuel pellets ready for reactors. Other techniques like co-precipitation also help mix elements at the atomic scale. Fuel fabrication is a blend of chemistry and engineering. The goal: safe, efficient, and reliable nuclear fuel. Let's look at the challenges and solutions in making thoria fuel. The science gets even more interesting. Making thoria fuel pellets isn't easy. Sintering is the key challenge. Sintering fuses powder pellets into hard ceramics at high temperatures, but pure thoria needs over 1,750 degrees Celsius. That's expensive and tricky for large-scale production. If pellets aren't dense enough, they can swell or deform in reactors, a safety risk. The solution? Add small amounts of other oxides like calcium or niobium to lower the sintering temperature. These additives make manufacturing cheaper and more practical. Real-world tests like those at Norway's Halden reactor prove these methods work. Engineers have created robust thoria fuels that perform well under reactor conditions. Innovation in material science is making thorium fuel a reality. Let's bring it all together. Thorium is abundant, globally distributed, and already being mined as a byproduct. The mining and extraction infrastructure is in place. Now we need to scale up thorium separation and fuel fabrication. Advanced techniques let us create high-quality, reliable thoria fuel. Challenges like high sintering temperatures have proven solutions. Real-world tests show thoria fuels are safe and effective. The next step: more testing, data, and regulatory approval for commercial use. Thorium offers a future of abundant, clean, and safe nuclear energy. The groundwork is laid and the resources are waiting. Now it's up to the next generation, maybe you, to turn this potential into reality. The adventure is just beginning. Will thorium power our world for centuries? The future is in your hands. Welcome. Today, we begin a journey into the future of energy, guided by nuclear physicist Kirk Sorensen, to explore the promise of thorium. Thorium could power our civilization for thousands of years, cleanly, safely, and with far less waste than today's reactors. This is not science fiction, but the result of decades of research and human ingenuity. Thorium is abundant, found in common rocks and sands, and its properties make it an exceptional candidate for nuclear energy. But potential isn't enough. Science demands proof. Our story starts with the creation of thorium fuel, small ceramic pellets that must withstand the intense environment inside a reactor. We'll follow thorium's journey from raw powder to high-performance fuel and see how scientists test its limits. This is more than a story about an element. It's about our quest for knowledge and a sustainable future. Join us as we step into the lab and the reactor core to witness the making of tomorrow's energy. To revolutionize nuclear power, we must first revolutionize nuclear fuel. Thorium offers clear advantages over uranium, but realizing its potential requires advanced materials science. Recent breakthroughs have enabled the creation of high-quality thorium-based fuels, ready for commercial use. The challenge: engineer a fuel that's powerful and stable under extreme heat and radiation. Scientists now control the fuel's microstructure, enhancing heat conduction and resistance to cracking. Mixing thorium with plutonium from nuclear waste creates a mixed oxide (MOX) fuel, turning a liability into an energy asset. These modern techniques are the result of years of trial and error, now allowing precise molecular-level fuel design. We're not just testing an idea, we're testing a refined, expertly crafted product. This foundation of advanced manufacturing is what makes thorium fuel testing so promising. The revolution begins in the lab, but its impact could reshape the world. The journey of thorium fuel starts with a fine white powder, thorium oxide. Scientists prepare this powder with exacting precision, as any flaw could compromise safety. The powder is pressed into a solid green pellet, using immense pressure, but it's still fragile. The magic happens: in sintering pellets are baked at over 1,700 degrees Celsius, fusing particles into a dense, robust ceramic. The result is a small, strong pellet engineered to withstand the rigors of nuclear fission. Each pellet is inspected for density, shape, and thermal properties. Pellets are stacked into zirconium alloy tubes, fuel rods, the building blocks of a reactor core. This process, from powder to fuel rod, is a feat of chemistry, physics, and engineering. The precision ensures safety and performance in the world's most demanding environment. Thorium fuel pellets may look unassuming, but they are marvels of modern science. They are ready for their ultimate test, the heart of a nuclear reactor. Perfecting a fuel pellet in the lab is just the beginning. The true test comes in the extreme environment of a nuclear reactor core. Here, fuel faces relentless neutron bombardment, intense heat, and radiation. Only real-world reactor testing can reveal how fuel swells, cracks, or releases gases under stress. Sensors track temperature, pressure, and structural changes as the fuel endures years of operation. This burn-up testing pushes fuel to its limits, measuring how much energy it can deliver and how it holds up over time. Research reactors like Halden in Norway are essential for this work, providing a controlled yet intense environment for fuel trials. These reactors don't generate electricity, they generate knowledge. By monitoring thorium fuel in real time, scientists gather the data needed to prove its safety and performance. It's the difference between theory and reality. Only through these trials can we transform a promising material into a proven technology. The reactor core is where ideas meet the ultimate test. For decades, Norway's Halden reactor was the world's premier site for nuclear fuel testing. Here, thorium fuels faced real reactor conditions, providing the first comprehensive data on their performance. Fuel rods were wired with sensors, measuring temperature, gas pressure, and structural changes in real time. It was like giving the fuel a medical checkup during a marathon. Thorium-plutonium fuels were tested alongside standard uranium fuels, allowing direct comparison. The results were remarkable. Thorium fuel showed better thermal properties, greater integrity, and improved gas retention. These weren't minor gains. They were significant advances in safety and efficiency. The Halden experiments provided the solid scientific foundation for thorium's promise. The data was clear: thorium-based fuels outperformed conventional options in key areas. This was the evidence the nuclear world had been waiting for. The Halden data told a compelling story. Thorium oxide's higher thermal conductivity means cooler, safer fuel pellets. Sensors showed thorium fuel retained fission gases better, reducing internal pressure and risk of damage. Even after intense radiation, thorium pellets resisted swelling and cracking, maintaining their shape and integrity. This stability ensures reliable, predictable reactor operation. Tests with thorium-plutonium MOX fuel were especially successful, proving it could safely consume plutonium waste. Thorium's advantages are hardwired into its physics: better safety, efficiency, and waste reduction. The numbers were consistent and clear. Thorium-based fuels aren't just an alternative, they're an upgrade. The evidence points to a better, safer nuclear future. The case for thorium is now built on solid ground. Beyond the lab, thorium fuel faced its biggest test at Germany's Obergheim power station. Here, thorium-plutonium rods ran alongside uranium fuel in a commercial reactor, generating electricity for the grid. The goal proved thorium could safely manage plutonium waste in real-world conditions. The results were flawless. Thorium fuel performed reliably for years, with no issues. Post-irradiation analysis confirmed the rod's structural integrity, matching lab results. Obergheim proved thorium-based fuels work in today's reactors, not just future designs. It showed thorium is a practical, safe partner for plutonium, reducing nuclear waste. This was real-world validation on a commercial scale. Thorium's journey from theory to proven technology is a triumph of science. Decades of testing at Halden and Obregheim turned promise into evidence. Data confirmed thorium's superior thermal performance, gas retention, and structural stability. Thorium fuels now match or surpass conventional uranium fuels in every key metric. This validation gives engineers confidence to design safer, more efficient reactors. Thorium's safety profile could help overcome public concerns and expand nuclear's role in clean energy. The success of thorium-plutonium fuels offers a new way to manage nuclear waste. By pairing thorium with plutonium, we can unlock energy from existing waste and reduce its long-term risks. These trials weren't just about a new fuel. They proved a more sustainable nuclear future is within reach. The foundation is set for the next era of innovation. We've seen thorium's journey from powder to proven fuel, validated by rigorous tests. The data is clear. Thorium is ready for real-world use, not just theory. Halden and Obregheim laid the groundwork for a new generation of safer, cleaner reactors. Thorium's success bridges the gap between promise and practical application. The next step: design reactors that fully harness thorium's unique properties, like the liquid fluoride thorium reactor, LFTR. These advanced designs could deliver even greater safety and efficiency. The story of thorium fuel is just the beginning. Our next chapter explores how liquid fuels and new reactor designs can revolutionize nuclear power. The cosmos gave us thorium. It's up to us to use it wisely. Join us as we continue unlocking the atom's power for a sustainable future. We've explored the thorium fuel cycle, a promising alternative to the uranium-plutonium path that's powered our world for decades. Thorium, abundant and versatile, can be transformed into uranium-233, offering the potential for cleaner, more sustainable energy with less long-lived radioactive waste. But scientific brilliance alone isn't enough. Any new technology must also be safe, secure, and economically viable. The shadow of nuclear proliferation materials falling into the wrong hands remains a central concern. We must also ask, can thorium compete economically? Can it deliver affordable energy? In this chapter, we'll dissect two critical dimensions: non-proliferation and economics. We'll examine the technical details that make thorium both secure and complex. We'll see how international bodies assess its risks and what safeguards are needed. Then we'll weigh the costs of mining, fabrication, and reprocessing against potential savings. This is where the dream of thorium meets the reality of engineering, geopolitics, and finance. Let's dive into what it means to responsibly harness the power of the stars on Earth. Splitting the atom gave us the power to build and to destroy. Non-proliferation is the global effort to prevent nuclear weapons spread. The uranium fuel cycle produces plutonium-239, a proliferation risk. Thorium's appeal: it doesn't produce plutonium but breeds uranium-233 instead. This led many to hope thorium could design out weapons risk. The International Nuclear Fuel Cycle Evaluation, INFCE, in the 1970s, studied this closely. INFCE found thorium's benefits real but not absolute uranium. 233 can also be weaponized. While harder to use than plutonium, the risk isn't eliminated. The path to a weapon is different, but not closed. INFCE shifted the narrative: thorium isn't a silver bullet, but a system with unique risks. Every nuclear fuel cycle carries some proliferation risk. The key is understanding each cycle's risks and building robust safeguards. No perfect solution exists, only layered, vigilant protection. Uranium-233 is the thorium cycle's star, an excellent fuel but also weapons usable. Fortunately, its creation comes with a catch: uranium-232 contamination. Uranium-232's decay chain emits intense gamma radiation, making the material hazardous to handle. This radiation acts as a built-in security feature, deterring theft and complicating weaponization. Over time, the gamma field intensifies, making handling even more dangerous. For legitimate operators, this means remote handling and heavy shielding, raising costs but boosting security. Yet this self-protection is a double-edged sword. The same radiation that deters proliferators also complicates peaceful fuel fabrication. Every step must be done remotely, behind thick shielding, unlike simpler uranium fuel handling. This radiological hazard is a fundamental trade-off: more security, but higher costs and engineering challenges. The thorium cycle's promise and complexity are inseparable. Security and practicality must be balanced at every step. Uranium-232's radiation is a deterrent, not an absolute barrier. A determined, well-resourced proliferator could overcome it with advanced technology. Some reactor designs could even minimize uranium-232, making uranium-233 more attractive for weapons. That's why international safeguards are essential. The International Atomic Energy Agency, IAEA, uses inspections, accounting, and surveillance to ensure nuclear material is used peacefully. For thorium, safeguards must track material from mining to reprocessing and fuel fabrication. The high radioactivity aids detection, but new measurement techniques are needed for uranium-233. Security relies on a multi-layered approach, technical barriers plus institutional oversight. Radiation slows down would-be proliferators. Safeguards increase the chance of detection. The thorium cycle doesn't eliminate the need for safeguards, it makes them even more vital. Only a combination of physical and institutional measures can create a formidable barrier to proliferation. Nuclear power's cost isn't just about building reactors, fuel costs matter too. The fuel cycle has two main parts: the front end, preparing fuel, and the back end, dealing with spent fuel. For uranium, the front end includes mining, milling, conversion, and crucially, enrichment, which is expensive and energy-intensive. Fuel is then fabricated into pellets and rods. The back end involves storing spent fuel, then either disposing of it or reprocessing it to recover usable material. Both strategies have significant costs and technical hurdles. Thorium's advocates point to savings: it's abundant and doesn't need enrichment. But a full economic analysis must consider the entire cycle. Thorium's unique properties affect fabrication, reprocessing, and waste management. Savings in one area may be offset by new costs elsewhere. The economic case for thorium is a complex trade-off. It's not just about cheaper raw materials but about the whole system. Let's break down where thorium could save and where it could cost more. Thorium is 3 to 4 times more abundant than uranium and often a byproduct of rare earth mining, making it cheap and accessible. Its biggest economic advantage: no need for costly enrichment since natural thorium is already the right isotope. This could mean major savings in infrastructure and energy. However, thorium fuel is harder to fabricate into pellets due to its physical properties. To start the cycle, a fissile driver like plutonium or enriched uranium is needed, reintroducing some uranium cycle costs. The real challenge comes with recycling uranium-233. Its intense radioactivity means all fabrication must be done remotely, in shielded facilities. This is far more expensive than handling fresh uranium fuel. The cost of remote fabrication could outweigh front-end savings. Thorium's economic promise is real, but not guaranteed. The balance between savings and new costs is delicate. The front end looks good, but the back end is where the real test lies. The back end of the thorium cycle is where costs and complexity soar. Reprocessing spent thorium fuel to recover uranium-233 must be done entirely by remote control, behind heavy shielding. The required infrastructure, hot cells, robotics, specialized maintenance, is extremely expensive. Chemically, thorium dioxide is tough to dissolve, making reprocessing harder than with uranium. Modified processes like Thorex exist, but they're less mature and more costly than established uranium methods. These challenges mean higher costs for reprocessing and waste management. For a once-through cycle, costs are lower, but resource efficiency is lost. Making thorium competitive will require major innovation in remote handling and chemical engineering. The thorium fuel cycle offers real promise: greater abundance, less plutonium, and built-in security features. But it's not a panacea. Uranium-233 is still weapons usable, and robust safeguards remain essential. Economically, thorium's lack of enrichment is a major plus, but back-end costs for remote handling and reprocessing are high. The chemical inertness of thorium adds further complexity. The path forward isn't a simple yes or no. It's a long-term commitment to research and innovation. Decades of uranium experience set a high bar for new technologies. For thorium to succeed, we need advanced reactors, better remote fabrication, and cheaper reprocessing. Thorium's story is a reminder: there are no easy answers in the quest for clean, safe, abundant energy. The potential is there, but realizing it will take patience, ingenuity, and global collaboration. The power of the atom is profound. Unlocking it responsibly is our challenge. The thorium dream is alive, but the journey is just beginning. Our task: keep exploring, questioning, and innovating. Special thanks to Professor Dr. Tarek Farouk Nagla, former research scientist at the Nuclear Power Plants Authority, Cairo, for his invaluable scientific contributions. Deepest thanks for Professor Dr. Tarek Nagla. Our cosmic journey has brought us back to Earth, to a defining challenge: our insatiable need for energy. We've tapped wind, water, and sun, but also unlocked the atom, releasing immense energy from its nucleus. This atomic power, born in stars, offers a path to a carbon-free future but with profound responsibilities. Nuclear energy is a story of promise and concern, of science, engineering, and human nature. As we seek cleaner, safer, and more sustainable energy, we must look beyond the familiar uranium cycle. Enter thorium, named after the Norse god of thunder. A metal with the potential to rewrite nuclear energy's rules. Thorium could be more abundant, efficient, and perhaps safer from misuse. But the real questions remain: can we keep it safe, and can we make it affordable? Thorium's story is entwined with these issues, offering solutions and new challenges. Let's explore how thorium's physics create barriers to weaponization and weigh its economic promise. This is a journey into the heart of the atom, seeking a power source worthy of a wise civilization. To understand thorium's promise, we must first confront nuclear energy's shadow proliferation. The risk is that nuclear materials or technology could be diverted to weapons. The same science that powers cities also built the atomic bomb. Fissile materials like highly enriched uranium-235 and plutonium-239 are at the heart of this risk, and are produced in many reactors. Any nation with nuclear power could, in theory, access these materials. Decades of diplomacy and technology have aimed to keep the nuclear genie in its bottle. No fuel cycle is perfectly proliferation-proof, but the goal is to make diversion harder, costlier, and easier to detect. The quest for a more secure fuel cycle is a direct response to this anxiety. In this context, thorium emerges as a compelling alternative. The thorium fuel cycle works differently from uranium's. Thorium-232 isn't fissile, it's fertile. It absorbs a neutron, transforms into protactinium-233, and then decays into uranium-233, which is fissile. Uranium-233 can power reactors, but it's also a potential weapons material, with a critical mass between uranium-235 and plutonium-239. This means thorium isn't inherently proliferation-proof. Uranium-233 could be weaponized if separated. However, the real non-proliferation advantage lies in what else is created: uranium-232. U-232 is produced in small amounts during the thorium cycle. Its presence, though minor, has enormous consequences. U-232's decay chain produces powerful gamma emitters, making the uranium-233 mixture intensely radioactive. This poison pill makes handling and weaponizing uranium-233 far more difficult and dangerous than traditional materials. So, while thorium isn't a perfect solution, its byproducts change the proliferation equation. The story is more complex than simple claims of safety. The real advantage is in the radioactive obstacles nature builds into the cycle. Let's see how this works. Uranium-232 is the thorium cycle's key non-proliferation feature. Its decay chain produces thallium-208, a powerful gamma emitter. These gamma rays penetrate shielding and are lethal to living tissue and electronics. The result? Uranium-233 from thorium is intensely radioactive, requiring heavy shielding and remote handling. This makes weaponization extraordinarily difficult. The radiation destroys sensitive electronics and poses a fatal risk to anyone assembling a device. This self-protection is a built-in deterrent. Unlike plutonium, which emits easily shielded alpha particles, U-232's gamma rays are a serious challenge. Any facility handling this material must be large, shielded, and conspicuous, hard to hide from inspectors. Nature's security system raises the bar for would-be proliferators. Self-protection is a cornerstone of thorium's non-proliferation case. The intense gamma radiation from U-232's decay chain deters theft and misuse. But this shield isn't absolute. Right after reprocessing, the radiation is lower. There's a brief window before the most dangerous isotopes build up. A sophisticated proliferator could exploit this window, working quickly before radiation becomes overwhelming. It's also technically possible, though extremely difficult, to separate U-232 from U-233. No technical fix is foolproof against a determined adversary. Self-protection is a strong layer of defense, but not a silver bullet. It makes diversion riskier, costlier, and more detectable, but vigilance and oversight remain essential. Because self-protection isn't perfect, international oversight remains crucial. The International Atomic Energy Agency, IAEA, verifies that nuclear materials are used only for peaceful purposes. For thorium, safeguards would adapt to its unique properties. tracking material from fresh fuel to spent waste. Intense radiation requires new monitoring techniques and remote sensors. Isotopic dilution, mixing U-233 with non-fissile uranium-238, can further deter weaponization, making separation even harder. This adds another technical hurdle for would-be proliferators. Thorium doesn't eliminate the need for oversight, it makes it more effective. The fuel's properties and international safeguards work together. Cheating becomes harder, more expensive, and more likely to be caught. This synergy is what makes thorium so attractive for a safer nuclear future. Now let's tackle the economics. Nuclear power's costs are dominated by massive upfront investments, long before any electricity is generated. These include capital costs for construction, ongoing operations, and managing fuel and waste. Building a nuclear plant is one of the most expensive infrastructure projects, often costing tens of billions and taking a decade or more. Thorium reactors, like molten salt designs, must prove they can be built more affordably than traditional reactors. Operational costs, staff, maintenance, security, are substantial even if fuel is cheap. Back-end costs like waste management and decommissioning add further billions. Thorium's economic promise lies in how it could streamline these expensive processes. Thorium's economic appeal starts with abundance. It's 3 to 4 times more common than uranium and widely distributed globally. This means a more secure, stable, and potentially cheaper fuel supply. Unlike uranium, thorium doesn't need enrichment, eliminating a costly, energy-intensive step. However, thorium introduces new challenges. Fabricating fuel is more complex due to intense radiation, requiring shielded facilities and remote handling. Reprocessing spent thorium fuel is also chemically challenging and expensive. These back-end costs could offset front-end savings. The final verdict depends on our ability to innovate and reduce these technical hurdles. Thorium's promise is real, but not automatic. It requires investment and engineering breakthroughs. Thorium offers profound potential, balanced by real challenges. Its fuel cycle's radioactive byproducts make weaponization far more difficult and detectable. While not a perfect solution, it's a significant step toward a more secure nuclear future. Thorium's abundance and lack of enrichment requirements could lower fuel costs and democratize nuclear energy. But higher costs for fuel fabrication and reprocessing remain obstacles. Realizing thorium's promise demands sustained research, development, and international collaboration. We need to build and test new reactors, refine reprocessing, and develop cost-effective remote handling. Thorium isn't a magic bullet, but it's one of the most intriguing options for clean, secure energy. The journey is long, but the potential rewards, a safer, more abundant energy future, are worth the effort. The cosmos has given us the ingredients. Our future depends on how wisely we use them.